Hello everyone, welcome back to Calculus BC. We're in lesson number 32 where we're talking about work. And in the first video we talked about work being defined as the integral from A to B of our force times our distance. So the force is going to be represented by the weight of the fluid and the volume of our fluid. And this D is going to represent how much we need to pump our fluid out. What's the distance the fluid is coming up out of our shape. And so I did a cone question in the first video, and I'm going to do that one again a little bit later on. I just want to go ahead and do another example of something I think is a little bit easier for us to do. In example number 4 before I go back to the cone question. So it says the tank contains 288 cubic feet of water. If the density of water is 62.4 pounds per feet cubed, how much work is needed to pump all the water out of the tank? All the water out of the tank. And then we're going to talk about that question first, and then we'll answer the second question. So we have two things we want to do here. So the first thing we got to do is we want to know how much water is actually in the tank. What's our quantity? Because it says our tank contains 288 cubic feet of water. Well, let's see right now what our volume of our actual tank is. So this is going to be the volume of the actual tank. Well, that's just going to be 8 times 12 times 4. And so if you multiply 8 times 12 times 4, you're going to get, and I have to use my little handy calculator here for a second, you're going to get 384 cubic feet. So this is how much water this tank can hold. We have 288 feet. So we want to know what that percentage is. So the volume of water in the tank is going to be 288 all over 384, which is going to give us 3 over 4. So this is 3/4 full. So our actual height of our water is actually going to be 3/4 of our tank. So this is going to be 3/4 of our tank right here. So we're not completely full with this. So what we want to do, why was that important? Well, we need to figure out, first of all, where the water level is. So remember, the A and the B is where the water level is. Well, we're at 0, and this is the height of our water. So here's our bottom of our water at 0, and then our height is going to be 3/4 of the height of our tank. So 3/4 of 8 is going to end up being 6. So that's how we're going to get this. So this, ladies and gentlemen, always represents where is the water in the tank before we do anything. And so 0, and then here. Now the students always ask, is this always 0? For most examples, yes. For example number 5, which we're going to do in the third video, the answer will be no, it's not going to be 0. But again, we'll get to that a little bit later on in life. Now, the next thing we got to do is we got to find the volume of one cross section. So let me really quickly get rid of all of this for 1 second. And so I want to do a cross section. And when I do that, I really want, and you guys can see that this right here would simply just be one rectangle, right? So it just would be one rectangle. So if I were to slice this thing down, I would have this little guy right here. So my volume is going to be a tiny little rectangular prism. So volume is going to be equal to our length times our width times our height. So the one beautiful thing about this is that our length and our width, it doesn't matter where we are, where this rectangular prism is, our length and our width are always going to be 12 and 4. So this kind of goes back into what we talked about with related rates, right? With related rates, where we can just automatically plug in stuff that's not changing. Now, remember, the height is going to be the height of this rectangle right here, this little guy. So remember, we talked about that. It's going to always be our dy. And, you know, if you want to just think about it again, we can say that this little guy is on the x-axis. And so the width, the height of this rectangle is just going to be our dy. So we can go ahead and do 12 times 4. So we're going to do 12, and we're going to do 4, and we're going to do dy. And remember, we also have to take into account the volume, but also then the weight of our actual function. So our weight of our fluid. So this is going to be times 62.4. Now, this, ladies and gentlemen, lets us know, are we done with our problem? Remember, our units are always going to be, in this particular example, feet and then pounds. So we want our answer to be pounds, feet. Well, this is going to be pounds per feet cubed. this is going to, sorry, pounds per feet cubed. This is going to be feet. This is going to be feet. And this is going to be feet. So you can see that these are going to cancel with this, and I'm just left with pounds. So I've got to do one more thing. And so this is just always an easy way to verify that you have one more thing we got to do. And that's going to be our displacement. We got to figure out what our D is. We haven't talked about the D yet. So everything that I've done right here represents our force. And again, it's the weight of our fluid and then the volume, simply the volume of one cross section of our figure. In this case, it happens to be a rectangle. And so our D is going to be, where's the water going? Where's the water going? So this again goes back to the shell method. So this distance is going to be y, all right? And I want to go, and it says I want to go above the tank, right? I want to pump it out of the tank completely, out of the tank. So I want it out of the tank here. So I want this distance. Well, this is 8, and I want this distance right here. This is what I want. This is the D. So the D is going to be our total, which is 8, minus our y. So then we have to multiply this whole thing by 8 minus y. And this is going to give us our other feet. And so now we have pounds per feet. So this is going to be the integral that we're going to do to find this actual work. So I'm going to go ahead and erase all of this and write it in a nicer format for us so you guys can see it. So our final answer for this particular part of the question is we're going to integrate from 0 to 6. 48 gives us feet squared. The 62.4 gives us our pounds per feet cubed. Then we're going to multiply all of this by 8 minus y, and then we're going to do dy. And so this is going to give us all our times. So again, weight of our fluid. This is going to be the actual volume of our cross section. This is how far the water's got to travel. And this is going to be, again, the distance that it starts versus the distance that it ends. Okay, so now the question says, how would my integral change if the tank is on one of the other sides? And then it says which position would produce the greatest amount of work. So you would use your calculator to find this out. So what I'm going to do is I'm going to pause the video. I'm going to write this as over here, and then we're going to do it the other way. Okay, so now we are going to talk about what happens if we turn it vertically. And so this is the integration. So not much is going to change here. Not much is going to change in this particular example. We're going to integrate now from 0. Now remember, we are 3/4. Remember, our water is 3/4 full. So 3/4 of 12 is actually going to be 9. So this means that our water level starting at 0, and it's actually up to the height of 9, because this again is 3/4 of our tank being full. Now our volume of our cross section, well, our width and our height, our width and our length are going to be 8 and 4, right? So we're actually going to do 4 times 8. So times, and now remember that our height of our cross section is going to always be our delta y. So this gives us our length times our width times our height. So remember, again, it's all about the volume of our cross section. We're going to multiply that by our density, which is going to be 62.4. And then all we have to do now is figure out how much the water is going to travel. Well, in this particular example, we're asking us again to go above, right? Above our tank. So we want to travel up 12. So our distance is going to be 12 minus y. The distance between here and here is y, and we want to go to 12, so our distance is 12 minus y. Another way of thinking about this, and it's just this I don't know if this is going to be helpful or not, is that the water that's right here at the very bottom of the tank, that has to travel 12 feet to get pumped out. So you know that you've done these two things right. If you plug in where the water is initially, so 0, you plug 0 into this, because this is also your displacement. This is going to be the displacement of your water as you guys do this. So if I plug in 0 here, this is telling me that the water that's at 0 level is going to travel 12 feet, which is exactly correct. And then if I go up here to where, the top of our water is initially, well, that's at 9 feet. So it's got to travel 3 additional feet to get out of the tank. Well, if you plug 9 into our displacement here, you're going to get 12 minus 9, which is going to give you 3. And that's going to tell you that this is also correct. That these two numbers are correct and this is correct. And so that's how you solve both these problems. I don't have the work in front of me, but you guys could use your calculators to figure out what this is, and whichever one is the higher is going to be the one that gives us the greatest amount of work. All right. I think that's a really good place to stop for this problem because I spent a lot of time talking about it. So we'll come back in video number 3 when we will now go back and revisit the cylinder question, and then we will talk about a spherical tank. So I'll see you guys back in the next video.